Okay, so hello everyone, I'm Qixi Liu, first year PhD student in Material Science and Engineering Department. Today we will talk about the image processing use Python, and all the material including this slide and the script are saved in the 18SDLE TTime repo in Bitbucket. So here is the outline for today. First, we will talk about the image and their properties, and then I will talk about some basic operation in Python, including the spatial filtering, edge detection, image enhancement, and the thresholding. We script to show how we do it in Python, and then is some application developed by my research group, including the planar indexing, defect detection, and the crack isolation. So let's first talk about image. All the image we see can be divided into two categories, vector images or raster images. Vector images describe the lines and the polygons in the image as mathematical equations, but raster image will describe the image as an array with color values. And they are very easy to distinguish from each other. If you enlarge an image, vector image won't get blurred, but the raster image will. When we do the image processing, we use Python, we treat the images as raster images, which means that the image is an array. So the first question is, since it's an array, how many columns and rows in this array? This question will be answered by a concept called pixel. In digital imaging, that pixel is the smallest controllable element of a picture represented on the screen. And all the colorful image we saw actually is composed of different color channels. We call it RGB, red, green, and blue. And together, these three channels build a colorful image. Here is an example. There is a smiling face. If I read this image into the environment, it will tell me that this array has 19 pixels in each row, 19 pixels in each column, and it has 3 color channels. This is how it looks like in different color channels. And when we want to extract some information from the image, we usually only choose one color scale. So for example, here is a grayscale, and this is a 19 times 19 array, and you can see there is value in each pixel. We call it intensity. Since each pixel is also marked by color, so you can still see the smiling face in this array. So the next question is, what's the range of the value of each pixel, which is the intensity? This question is answered by another concept called bit depth. The pixel range of a given image format is determined by the pixel. It is defined by this equation. And the image we usually saw is an 8-bit image, which means that the range is from 0 to 255. And for medical and some microscope images may have higher bit depths. It means that it will have a wider intensity range because it has higher requirement of the accuracy. And since now we know the range, the next question is, what's the distribution of the intensity value? This question is answered by the histogram. The x-axis is the intensity value, and the y-axis is the frequency. So the histogram will tell us the distribution of the intensity value. And now, if I get an image, there is first 4 parameters I need to know. What's the bit depth, how many pixels it has, and the image histogram and the image type. Actually, besides these 4, we also have 3 parameters as basic parameters. They are the voxel, window and level, and the connectivity. Voxel is related with how to make the 3D object show correctly in the 2D picture. And the window and level is for user to adjust the contrast of an image. And the connectivity is a very useful concept for Fourier transformation. Since these 3 properties is not very useful for today's topic, we won't go too detail for them. So since now we already have some basic understanding of the image, it's time to do something to it. The image process can always be summarized into these steps. First, read the image into environment, and then do something to it. And then you can choose to write the image or to show the image in the console. And the low-level image processing refers to the operation operate on each individual pixel. Actually, because it operates on each individual pixel, so it's very general. And all the operation we will introduce today can be classified as low-level image processing. And the high-level image processing must be based on the understanding of the image. So it's not very general. And the typical example is pattern recognition. And we have one example in the application part. So first operation we will introduce is the spatial filtering. Let's first talk about what is filtering. Filtering is used to remove noise or undesirable impurities. And it can also be used to determine the edge of an object. There are two types of filter, linear filter and nonlinear filters. And it can be accomplished in two domains, spatial or frequency. And the spatial filter is what we will introduce today. And the frequency domain filter is the Fourier transformation. So now let's see how the spatial filter works. The image is a pixel. It first defines a small moving window that works on one pixel at one time. And all the pixel value under this small window are collected. And based on different method, it has different cutoff value. And if the pixel value that this window is working on is lower than the cutoff, it will be replaced by the cutoff value. Like for the mean method, that the cutoff value is the mean value of this small area under the window. And you can guess what the cutoff value is for the rest method. And actually, we can test this theory, this understanding by the Python function. But for the mean filter, since it has a very big disadvantage, so it's very rare to use it. I haven't found already built function for the mean filter, but all the rest method that has function that in the SciPy ND image. Now let's go to the script to test this theory. I'm working in Spider. Okay, so let's start with at the very beginning. First, we import all the useful modules to my environment. And then I give the directory of my figure to dir. And I assign the file name to file. Join these two parts will give me the whole path of my image. And then I use the image open function to read the image into my environment. And we can see this image here. It's a grayscale smiling face that is very small. And then I transfer this image to an array, use the from image function. And here you can see this array. And this part is about how to make the image histogram. Here you can see the distribution of the intensity value. And now this part to test our theory. The pixel 55, the value is 169. And the filter convolve works similar with mean filter, but they are not exactly the same. So it can't give you the result as the theory. Yes, it's 195, but actually it should be 187. But for the other method, that for the mean filter, max filter, minimum filter, that already have the function built in this module, yeah, the result is exactly the same as what we calculate by hand. Yeah, they are exactly the same. And actually, we can guess the effect of the filter by the theory. For example, the mean filter. First, it makes the pixel value become more closer with its neighbor, so it will blur the image. And besides, it will assign all the value under the mean value to be the mean value, so the image will be slightly brighter. This page is about the characteristic of each spatial filter method. Here is an example. There is a strawberry with a black frame and some dark point that it on purpose as noise. So after mean filter, we can see the black nodes are faded, but the whole image gets blurred. And after median filter, the black points are gone, and it looks good. And the max filter works to enhance the brighter points in an image. So we say the whole strawberry become brighter, and the frame, since it's black, is become thinner, and the seed in the strawberry become bigger. And the noise point, since it's black, so it's gone, because it will enhance the bright points in the image, which means that it will reduce the black points in an image. And the minimal filter works to enhance the darkest point in an image, so the black points become bigger, the frame becomes thicker, and the strawberry become darker, and you can see the seed actually becomes smaller. We can go to demo to show how we get those images. It works very easy. First, still read those images into the environment. This is a raw image of that strawberry. And here I use the filter convolve as the main filter. And you need to define the size of the moving window by yourself. And for the other method, there is a parameter called size, which is a parameter to define the size of the window. 5 means it's a 5 times 5 window. So the next operation is edge detection. Why the edge can be detected? It's because the parameters of edge is different with the rest area. It's present in the intensity, first derivative of the intensity and second derivative of the intensity. Here is an example. There is an edge between the black area and the white area. And for all the black area, the pixel value are 36, and for white area, the value is 255. And for the edge areas, the pixel value changes slowly from 36 to 255. So if you plot the intensity value from the left to the right, it will change in this way. And here is the first derivative, here is the second derivative. So it's very obvious to say that the edge has different parameters as compared with the rest area. But actually, in most open cases, the edge condition is very complex with noise. So there are a lot of methods developed to work on different conditions. Here I show the Laplace Gaussian, Sobel, and Prewitt. There are 4 methods to do the edge detection. And this tool is worked on using the horizontal direction, and this tool is worked in the vertical direction. The horizontal direction can make the edge horizontal to be deeper to see, and the vertical direction edge detection can make the vertical edge to be more deeper to see. And we can go to demo to see how we get those images. First, still raise the image into the environment. And then change it, transfer it to the array. And the Sobel Prewitt are in the SciPy is in the scale image module, but the Laplace and the Laplace Gaussian are in the ND image module. It's very easy to get those images. It's just very simple function. And you may notice that the ND image filters Laplace and the ND image filters Gaussian Laplace have a parameter called mode. This can change like as reflect or constant. Actually, this parameter is still with the edge of the image. So the next operation is image enhancement. Actually, filters, edge detection, they are all methods to work on image enhancement. The things we mentioned here are specifically refers to using mapping function. It's like we apply a function to each individual pixel to do a transformation. And since it's applied to all the pixels, that's the reason we call it mapping function. And because of it has different format of the equation, so it has different names. We can show 2 of them in the script. I choose the image inverse and the image stringing. Here. And you may notice that the B actually is an array of the image, and this function here is a mapping function for image inverse because it applies to each individual pixel in the array, and this function is for the construct stringing. And the last operation we mentioned is thresholding. It works to unify the background, and it always works in this way. First, give it a threshold value, and if the pixel value is larger than the threshold value, then do operation 1, else do operation 2. And there is already exists a lot of function for to choose the operation 1 and operation 2. And if the image histogram has 2 peaks, there is a function called OTSU to automatically return you a value to separate these 2 peaks. For this, I use an example of a cell image. Okay, so this is electroluminescence PV cell image. We care about the dark area in this image, so I want to do a threshold to unify all the area that is not dark to be white. So let's first take a look at of the image histogram. It seems like it has 2 peaks. One is here, and another is in this area. This is the right histogram. That's why I feel it's strange. We didn't update the array B. Now this is the histogram for the cell image, and it seems that if we want to separate these 2 peaks, the threshold value should be around 100. Now let's try to test the OTSU method. Yeah, it returns as the value is 96, so it's very close to 100 and can be worked effectively to separate these 2 peaks. And here is the threshold result. If we compare it with the raw image, you can see the very dark area in the raw image now become totally dark, and all the rest area become white. And we have a lot of choices for the operation 1, operation 2. What you want to do if the pixel value is larger than the threshold, and what you want to do if the pixel value is lower than the threshold. We still use this cell image as an example. Okay, so here you can see you have different choices to do the threshold. So now we move to the application part. Our research group that has a project called MALIT. The full name is Module Level Evaluation and Test. And this project working on the degradation study of the PV module. And we need the image processing to work on the electroluminescence PV module image. And here is one electroluminescence PV module image. Sometimes because the camera and the module is not parallel with each other, so the module part in the image is not a rectangle, but we want it to be. So here is the planar indexing pipeline developed by Justin. First, it do a median filter to remove some noise in this raw image, and then it do a background threshold to unify all the background to be totally black. And then it run a convex tool to find the main part of the edge in the 4 edge and then it ran a linear regression to find the change point as the corner position. And then based on the corner position, it ran a perspective transformed. So after one raw image goes through this pipeline, we got the module image as a standard rectangle. And the next part is about my defect detection. Here is one EL cell image. What I want to extract it from this image is the average width of this dark edge. And the average width of these three thin lines, we call it bus bar. And the size and the position of the dark points. So I first do a threshold, and then I calculate the average width of the dark edge and then remove it from the image. And then I calculate the average width of the bus bar and then remove it from the image. Now there is only dark points in this image. I do an image inverse and then do a pattern recognition, which we mentioned in the front that is a high-level image processing operation. And then after this operation, the information of one cell is saved in a date frame. So one cell have one date frame that saves the average width of the bus bar, average width of the edge darkening, and all the dark point position and size. The last application is crack isolation that's developed by Nick. It uses the thresholding, open and close image and color inverse to isolate the cracks. So you see this image that has a lot of things. That's the dark edge and the bus bar and a crack. But we want only the crack. So it works in this pipeline to get only crack in this image. And finally, thanks to the Department of Energy and the support from the HPC. That's all. Any questions?
What do you do after you've done this image processing?
Usually, like for my defect detection, actually you need to use those data sets to build a model or run the hypothetical test. Like actually, all the cell images is get from the module image, and the project topic I'm working on is to test whether the edge area has more defects or the center area has more defects. So this is just a process that we want to get the data from the image, and there are a lot of work that need to be done in the data set, like build the model, do the visualization, or the EDA. Yeah, the first process is get the data from the image, and this is what the image processing is working on.